So on to example 4, we're looking at a Taylor polynomial. This time it's not Maclaurin because the Taylor polynomial is not centered at 0, it's centered at 1. All right, so we're going to use the function natural log of x, and because this says n equals 6, we're going to have to take 6 derivatives here, so hold on to your seats here because this is going to be a kind of a longer problem. And I'm going to go ahead and write that derivative as a power because powers differentiate very nicely. We will bring the negative 1 out front and multiply or change the exponent to negative 2. We're going to bring that negative 2 out front. Negative 1 times negative 2 is positive 2. And then we just continue on with this pattern. And as you build this, you should notice some familiar values showing up as the coefficients. If you don't recognize those, then go back and review some interesting functions that we've learned recently, and you'll find that these are actually important numbers that we know about. Anyway, we're not going to evaluate these at x equals 0. We can't because natural log of 0 is undefined, 1 over 0 is undefined, 1 over 0 squared is undefined. That's good news because we're actually going to evaluate this at 1. X equals 1. We're still going to take f of 1, which is 0, f prime of 1, which is 1 over 1, which is 1, f double prime of 1, which is negative 1 over 1, which is negative 1, f triple prime of 1, which is 2 over 1, which is 2. And you're going to notice this 1, this x value of 1 is actually very nice because 1 raised to any power is going to equal 1. So all we end up with is whatever that coefficient is from all of those repeated power rules. All right, so each one of those values is going to fall into the coefficients, numerators of each of the terms of P6. So P6 of x equals, our first value is 0. So we've got 0. The next term is 1, so plus 1 times x. But it's not x, is it? Because we're not centered at 0, we're centered at 1. So we want to make sure that anytime I put an x in here, I have it as x minus 1. Think about point slope form. Y minus y1 equals m times x minus x1. Our x1 value in this case is 1, so we want to make sure we have that in there. And that's raised to the first power. I'll go ahead and write that for fun. The next coefficient is negative 1, so we put that negative 1 on the top. We put a 2 factorial on the bottom, and now we've got x minus 1 raised to the 2. Our next coefficient is 2, so I'll put that on the top and the 3 factorial on the bottom, and we've got x minus 1 raised to the 3. Our next coefficient is negative 6, so I'm going to put a negative 6 on the top and a 4 factorial on the bottom, and then have x minus 1 raised to the 4th. And then our next coefficient is 24, so I'm going to put plus 24 over 5 factorial times x minus 1 raised to the 5th. Lastly, we have this negative 120. Let's see, positive, negative, yeah, good. So we've got a negative 120 over 6 factorial, x minus 1 raised to the 6th. All right, so if you haven't already noticed, now is the punchline. These guys right here are factorials, right? So 5 factorial is 120, 4 factorial is 24, etc. So these are really nice to put in the numerator of factorials because they reduce. So we end up with 0 plus 1 times x minus 1, and then minus 1 over 2, because 2 factorial is 2, times x minus 1 squared. 2 over 3 factorial is just 1/3, and we've got x minus 1 cubed. 6 over 4 factorial is 1 over 4, and this is a negative 1 over 4, and we see a really pleasing, easy to see pattern. 4 factorial over 5 factorial, that's just 1/5. And you can imagine how easy it is to continue this on past the 6th term, or the 6th degree. And you can make these as long as you would like, and you can play around in Desmos with the summation notation, and you can see higher and higher degrees starting to hug the natural log of x function better and better and better, at least in a certain interval. More on that later. So it asks us to use this polynomial, this degree 6 polynomial, to approximate the value of natural log of 1.1. The natural log of 1.1 should be approximately equal to p sub 6 of 1.1, which is equal to, let's see, 1.1 minus 1 is 0.1. Minus 0.1 squared over 2 plus 0.1 cubed over 3. plus 0.1 to the fourth over 4 plus 0.1 to the fifth over 5 minus 0.1 to the sixth over 6. And if the mood strikes you, punch that into a calculator and compare how incredibly close this is to this. Maybe not incredibly close, but they should be at least pretty close. Maybe incredibly close. I'd have to do it to find out. But anyway, we know that they are approximately the same because that degree 6 polynomial is going to be a good approximation for the natural log of x, at least for x values close to 1. And I would call 1.1 fairly close to 1. All right, so that's a nice example, a nice pattern that we want to kind of be familiar with. This next example doesn't give us a function, but it does give us some values at x equals 2. It gives us g of 2, g prime of 2, and g double prime of 2, and even g triple prime of 2. So this actually does a lot of the work for us. All this stuff that we did in purple up here and green up here, we don't have to do that because it's been done for us. So all we have to do is build the Taylor polynomial. So we're going to find the degree 3 polynomial, so I'll call it p sub 3. And I just have to find g of 3. Oh, I found it. It's 3. I'm going to have to find g prime of, I'm sorry, not g of 3, but g of 2. And it's equal to 3. G prime of 2 is equal to negative 4. So if we had stopped right there, then don't forget this is not x, this is x minus 2, right? That's the tangent line, y1 plus m times x minus x1. We've been doing that all year long, but we don't stop there because we want the degree 2 term, so that's going to be plus 7, but don't forget that 2 factorial on the bottom, and then x minus 2 squared. And then we take one more step and we take f minus 5, and over that's over 3 factorial, and you've got x minus 2 cubed. And guess what? You're done. It doesn't ask you to do anything else. So moving on. With this limit, we should recognize this as perhaps a L'Hopital problem. We can definitely do L'Hopital's rule on this, and it would take a matter of seconds. But let's kind of explore this new world for us and use a Taylor approximation of e to the x. E to the x is the nicest one to look at because when you take e to the x and you take its derivative, you get it back again. So it never ever changes. So if we take this to the third derivative, we still have e to the x. Evaluating this at 0, we have f of 0 equals 1, f prime of 0 equals 1, f double prime of 0 equals 1, f triple prime of 0 equals 1. So e to the x is approximately equal to 1 plus x squared over 2 plus x cubed over 6, right? That's 2 factorial is 2 and 3 factorial is 6. So I'm going to say that the limit as x approaches 0 of e to the x minus 1 over 2x is approximately equal to the limit as x approaches 0 of, instead of e to the x, I'm going to replace it with this guy right here because they're approximately the same, at least when x is close to 0. So we're going to put 1 plus x squared over 2 plus x cubed over 6, and then that's this part right here. So then minus 1, that's the other part of that numerator, divided by 2x. And if I simplify this, the 1's cancel out, so I've got the limit as x approaches 0 of x plus x squared over 2 plus x cubed over 6, all divided by 2x, and there's a common factor of x that we can divide out, and if we do that, we get 1 plus x over 2 plus x squared over 6 divided by 2, and now that the x is canceled out, I can see that I'm left with 1 plus 0 over 2, or 1/2. So that's a long way to go to get the same answer you would have gotten if you had just done L'Hopital's rule, but you actually can see that this works out to be the same thing. Perhaps it's surprising that it's not approximately equal to, but is actually exactly equal to that limit. But when you think about how x is approaching 0, and these guys are so close to being the same thing, especially when we're very close to 0, that we end up not actually even changing the limit when we use this process.